So now that we have seen the definition of measurable functions, and we have also seen some basic properties of measurable functions, so it's now a good time to have some intuitive idea of what a measurable function should be and what pointwise convergence of measurable functions should be. So this is encapsulated in what are called Littlewood's principles. We have already seen one Littlewood principle when we were defining Lebesgue measurability, which said that every measurable set, so I am putting measurable in brackets because the idea is to write that every set is almost open, and this is what we used to define Lebesgue measurability. And in fact, we can also say something stronger, which is that every set is almost a finite union of boxes, or in the one-dimensional case, intervals. So here again there is some catch, which is that it should be a measurable set with finite measure. So it's actually a nice exercise to show that every measurable set with finite measure can be approximated with respect to the symmetric difference with a finite union of boxes, and such that the measure of the symmetric difference of the set with this finite union of boxes is less than or equal to some given epsilon. So in this way, Littlewood's first principle gives you an idea, an intuitive idea of what a measurable set should look like and what a measurable set with finite measure should look like. So then Littlewood's second principle says that every function is almost continuous, and here also the catch is that it should be a measurable function, or we will see that it also works if it is a Lebesgue integrable function. So once we define what is a Lebesgue integrable function, we will see that these functions are almost continuous. So of course we have to make precise what are these, what is meant by these almost, but we will see that it is up to some epsilon or up to some finite tolerance in the measures. We have to state these properties for being almost continuous and almost open. So the second principle says that every measurable function or a Lebesgue integrable function is almost continuous. So you can view a measurable function as a continuous function outside a set of negligible measure. On the other hand, the third principle says that every convergent sequence of functions is uniformly convergent. So again there is a catch, which is that it should be a pointwise convergent sequence of measurable functions, and here in general one can only have uniform convergence locally, which means that it will be uniformly convergent once you take the intersection with a bounded bounded Euclidean ball. So these three Littlewood's principles gives us some idea of how one should think about pointwise convergence of measurable functions, how one should think about absolutely integrable or measurable functions, and how one should think about measurable sets. So in this lecture we will see the third point, which is that every pointwise convergent sequence of measurable functions is uniformly convergent. So this is known as, this result, when you make it precise, is known as Agarose theorem, and we will see what is the Egorov theorem, and we will try to prove it in this lecture. So let's see the statement of Egorov theorem. So we start with a measure space x b mu, and we take a sequence of measurable functions fn defined on a measurable set E with finite measure mu e, and assume that fn converges pointwise to some function f on E. Then Agarose theorem states that given epsilon greater than 0, there exists a measurable function a epsilon, which is a subset of E, measurable subset of E, such that the measure, so here it should be mu, measure of E minus a epsilon is less than or equal to E, less than or equal to epsilon, which means that the complement of a epsilon inside E has very small measure, and Fn converges to F uniformly on E. So recall that Fn converges to F uniformly on a epsilon means that for any epsilon greater than 0, so this epsilon is different from the given epsilon, so let me take something else, some eta greater than 0, there exists a number, natural number n, such that, let me write n naught, such that modulus of fn x minus fx is less than eta for all n greater than or equal to n naught and x in a epsilon. So the point is that here the difference between uniform convergence and pointwise convergence is that we can choose n, this n naught, this is independent of the chosen point x. So this holds for all x in this is for all x in this set A epsilon. So we see that outside a set of measure less than or equal to epsilon, we have uniform convergence, and this is what Littlewood's third principle says, that every pointwise convergent sequence of measurable functions is uniformly convergent. So of course we have to make sure that our assumptions are correct, which is that it should be, this convergence should be on a measurable set with finite measure, and then we can make the statement that it is uniformly convergent outside a set of measure less than or equal to epsilon. So let's see the proof of Egorov's theorem. Proof. So we define for each n a natural number and k a natural number, E n k, which is the set of all points in E, such that the modulus of f jx minus fx is less than 1 over n for all j greater than k. So we are looking at those points which become close to, for which fjx becomes close to fx for all j greater than k up to a tolerance of 1 by n. So this ENK is a measurable set for each k greater than 1 and n greater than 1, because first of all this is fj minus f is a measurable function because fj's are all measurable. So this fj minus f is a measurable function. On the other hand, it is a composition with the continuous function which is the modulus. Therefore, the modulus of fj minus f is also continuous, is also measurable. So we are taking the inverse image. So ENK is the inverse image of the function fj minus f mod of the set of the interval 0 to 1 by n, which is open at 1 by n. And of course this is a Borel set, and so this is a measurable set. Of course one should take the intersection with E, because the ENKs should be a subset of E. Nevertheless, E is measurable, so ENKs are all measurable. Now we fix n, then we have that ENK is a subset of ENK plus 1, because if this inequality holds for j greater than k, then it also holds for j greater than k plus 1, and so we have this inclusion of ENK inside ENK plus 1. On the other hand, since Fn converges to f pointwise, so any x in E lies in ENK for some k. Fixing n, we can always find a k large enough such that x belongs to ENK, because Fn converges pointwise to f, so this difference fjx minus fx modulus is going to be less than 1 by n for a large enough k. So we have that this implies that E is a subset of the union of all these ENKs, k equal to 1 to infinity. And since ENK is a subset of E, by definition we are only taking points in E, which implies that E is actually equal to the union of all these sets ENK. So this is for any fixed n, for any fixed n greater than or equal to 1. So now I am going to use the upward monotone convergence theorem, which states that the measure of E is equal to the limit as k tends to infinity of these sets mu ENK. This is the statement for the upward monotone convergence theorem. This implies that given epsilon greater than 0, there exists a number k, which I will write k as kn, belonging to the natural numbers, such that given n greater than 0, n a natural number, there exists a number kn such that we have that the measure of the set E minus En kn is less than or equal to 1 over 2 to the power n. Because of this limit condition, because of this upward monotone convergence theorem, we have this, and this is nothing but mu E minus mu En kn. So by construction we have that for any x belong to En kn for some n greater than or equal to 1, we have that the modulus of fjx minus fx is less than 1 over n for all j greater than kn. This is how we define the sets E and k, and so this holds by our construction of the sets E and k. Now choose capital N in the natural numbers such that 1 over 2 to the power n minus 1 is less than or equal to epsilon. So given epsilon greater than 0, we choose a natural number n, capital N, such that 1 over 2 to the power n minus 1 is less than or equal to epsilon, and note that 1 over 2 to the power n is nothing but the sum from n to infinity 1 over 2 to the power k, and this is less than or equal to epsilon. So we put now A epsilon is now defined as the intersection of the sets n greater than or equal to capital N of E n kn, which means that any pointing A epsilon lies in all of these E n kns for n greater than or equal to this capital N. So then we can estimate the measure of E minus A epsilon, which is equal to the measure mu, which is equal to the measure mu of E minus the intersection of n greater than or equal to capital N E n kn, and this is equal to the measure of E intersection n greater than or equal to capital N E n kn complement, and this is equal to the measure of E intersection the union n greater than or equal to n E n kn complement, which can be written as the union n greater than or equal to capital N E minus E n kn, and this can be made smaller than the sum n equal to capital N to infinity. So this is these are from n to infinity. So capital N to infinity measure of E minus E n kn, and each of them was less than or equal to 1 over 2 to the power n. So this is less than or equal to the sum n equal to capital N to infinity 1 over 2 to the power n, and this is precisely 1 over 2 to the power n minus 1, and we have chosen this to be less than epsilon. So on this outside this set A epsilon, the complement of A epsilon in E has measure less than or equal to epsilon. So now we claim that f n converges to f uniformly on A epsilon. So in other words, given eta greater than 0, there exists a number n naught in capital N such that modulus of fj or fn, let's say fnx minus fx is less than or equal to eta for all n greater than or equal to n naught and for all x in A epsilon. So this is the definition of uniform convergence for points for the set on the set A epsilon. Now recall that A epsilon was in fact the intersection of these E n k n's, which means that if x belongs to A epsilon, then x belongs to E n k n for all n greater than capital N, and we have that fj x minus fx modulus is less than 1 over n for all j greater than kn, and this holds for all n. So this is for all n greater than or equal to n. There exists a number kn such that this holds because x belongs to En kn. And so now if given eta greater than 0, we choose n greater than or equal to capital N such that 1 over n is less than this eta, and set n naught to be this kn that we get from fixing an n and then getting kn. So we have for any x in A epsilon that the modulus of fjx minus fx is less than 1 over n naught 1 over n, which is less than eta, and this holds for all j greater than kn, which is n naught, and this proves that fn converges to f uniformly on A epsilon. So we have shown that given a pointwise convergent sequence on a set of measurable set of finite measure, then we can find an exceptional set A epsilon. We can find a set A epsilon on which it converges uniformly, and the exceptional set for which it doesn't converge uniformly has a measure as small as we want for a given tolerance level epsilon. On the other hand, we remark here that we cannot upgrade to the case mu e minus A epsilon equal to 0 and such that fn converges to f uniformly on A epsilon, because we take this example, functions defined on R and taking values on R, and in fact we don't need it to be defined on the whole real line, we will only define it for 0 1, and it will also take values in 0 plus infinity. So fn of x is defined to be 1 over nx for x belonging to the interval 0 1, which is open at 0 and closed at 1, and 0 for x equal to 0. So we have defined a sequence of functions on a set of measurable set of finite measure, which is 0 1, and these are all non-negative unsigned measurable functions. So we can show that Fn converges to the 0 function on 0 1. This is pointwise. This is pointwise convergence. Now suppose that there exists a set A. So here there is no dependence on epsilon, so you can remove it here. Suppose that there exists such a set A on which Fn converges to F uniformly, and the measure of E minus A is equal to 0. But if we have uniform convergence, then there exists an n naught belonging to n such that Fnx, the modulus of Fnx minus 0, so you can forget about that. So just the modulus of Fnx is less than or equal to epsilon for all x in A. So for any epsilon greater than 0, we can find an n naught independent of the point x, such that this holds for all n greater than or equal to n naught and for all x belonging to A. But the modulus of Fnx cannot be small if you take x is taken to be 1 over n naught, then the modulus of Fn naught x is equal to 1 over n naught times 1 over n naught, which is simply 1, and so it violates this condition. We get a contradiction. Therefore, the measure of the set E minus the set on which there is uniform convergence is at least greater than or equal to 1 over n naught. Therefore, we cannot hope to have measure 0, the exceptional set to be measure 0, outside of which there is uniform convergence.